which end of the conducting wire will be negative and which one will be positive. So basically, like, which way will the electrons be flowing? So here we're told our B is going into the page, okay? And our V is going this way. So in order to do like force or induce that current, we're going to have to force it in the opposite way. So like we're going to have to do work on it. So the first thing you write in is that your FM needs to go in the opposite direction of where you find your V. Okay? So now, that's the FM to oppose the original motion. So we're going to be using, we'll use our left hand because we're not told that it's conventional current. So B is going, it's going into the page. Our FM is going up. So our current flow is this way, okay, to the left. Okay, so here we'll have our current flow going that way. So then this end will be negative and this end will be positive. So this is our third hand rule. And this is FM to oppose. Go ahead. You have a question? Pardon me?
Because if your thing's going down,
so B,
and your FM is up, like if you do it like with a hand like this, it depends which way you have your hand.
no, because your
Fingers in my FM.
okay. So it's like if you have your B is going in and your F is going up, these go up. Goes that way. Maybe I'll do another one and then we'll come back to that one. Okay, another example. This picture shows an induced current flowing through a solenoid due to a magnet moving in relation to the solenoid. Determine which way the magnet needs to move to produce the induced current as shown in the diagram. Okay, so what we need to think is this magnet is moving in relation to this one, and it's asking us which way does it need to move. Does the magnet need to move this way or this way to induce to produce the induced current shown? So the induced current shown is wrapped around. So this is our second hand rule. Okay, so we have our second hand rule. It's coiled around. So if that induced current's going this way, then our thumb points towards the north end. So here's north and here's south of the magnetic field that's induced in the solenoid, or that's in the solenoid. Then, so now what we need to think is which way, think about these almost as two different magnets. Which way do you need to move the magnets in order for work to be done? So, well, first here, let's see. Which way, if you put these two magnets together, which way would they go? They would want to be forced apart, right? Like they would be repelling. So, here, the magnetic force that it would experience would be to pull it, like to push them apart from each other. Okay? So in order to do like the opposite, like to do work on it, you're going to have to force it the opposite way. Okay? So the motion that you're going to have to move the object is this way. Okay? So
You mean the motion?
the motion that you have to push the magnet in order to induce a current.
So we?
No, not, yeah, the way that you have to move it, yeah.
Why don't you just flip it and then they interact?
What do you mean?
Well, if you're going to push it, FM's still going to go the same way, will it not?
If I'm going to push it. Yeah, so they're going to be forced to go this way, but if you're pushing it that way, you're doing work on it. Like if you just kept pulling it apart, there's no work being done.
You wanted to change the direction of it. You said you didn't want FM going that way.
No, FM has to go that way. If I have two magnets that are like this, FM will always go that way. So, because the question is asking me, determine which way the magnet needs to move to produce the induced current.
So it would always be toward the solenoid.
No, not necessarily.
Well, if you brought it away, then it just do its own thing.
But what if the current was different?
I don't know.
Okay, that's why I'm saying it doesn't always need. It's not always the same.
So if it was attracting already, if FM was the other way, then your motion would have to be the other way?
If FM was the other way, then your motion would have to be the other way, yeah.
So you're trying to kind of fight the magnetic.
Exactly. You're trying to fight the magnetic force that would originally happen. Just like in the other example, if the motion is all originally in one direction, you're saying what the other force is. So like with these ones, did I already do that? Up here? Oh yeah, so like this FM, if it's going in that direction, the motion would be originally going that way. So like with this one, you have to force, you're working against the magnetic force, yeah, that's experienced. So just, yeah, in summary, if FM is pushing the magnet away, or like to the left, thinking about just like this magnet that I get to move, then motion was to the right. So kind of another solenoid one. So this might answer some of your questions. So next we're asked to predict the direction of the induced current. So if the motion is going this way, okay, if to induce a current, if I'm to pull it up like this, I'm working against a magnetic force. So my FM must be going in the opposite direction of your motion. So if FM is pulling these two magnets together naturally, then this end must need to be north, and this end would be south. So this is FM to oppose motion. This is saying opposite poles attract. So now, again, we're going to have to use our second hand rule because we have a coil. So put your thumb in the direction of north, and then you have your coils coming around. So the direction of our electron flow is as so. So we can draw that in. Now, if we wanted to kind of show it even more clearly, you can show it here, right? So if the electrons are going this way, that means it's flowing like this, okay, coming in, out.